So we've seen that the number of heads on 4 flips of the coin can be any number from 0 through 4. So the number of heads, $H for number of heads, is from 0 to 4. Frequency is the number of times they occur. Now the frequency, and I didn't have room to write it, this would be the ideal frequency. The ideal frequency on 16 flips would be to get 0 heads 1 time, 1 head 4 times, 2 heads 6 times, 3 heads 4 times, 4 heads 1 time, as we saw in the preceding video. Meaning that the probability of getting no heads is 1 out of 16. There's 1 way out of 16 to get no heads, 4 ways out of 16 to get 1 head, 6 ways out of 16 to get 2 heads, and so forth. And of course, 4/16 reduces to 1/4, 6/16 to 3/8, etc. And we have decimal equivalents. We know the decimal equivalent of 1/4, of course, is 0.25. Everybody should know that the decimal equivalent of 3/8 is 0.375. And if you don't know that, you should be able to divide that in your head. And if you can't, it's because you had a calculator in your hand too many times, and you need to start doing things like that so you develop a little mental arithmetic, a little better sense of the numbers. And 1/16, which is also fairly easy to do in your head. 16 times 6 is 96, leaving 4. 4 over 16 is 1/4. You find that this is then 0.0625 after a little thinking. Okay, now what we want to know is then what would be the standard deviation of the number of heads that you get if you get the ideal frequencies. So we can do that by saying, okay, well, let's assume we get 0 heads 1 time. We get 1 head 4 times, so we get a 1, a 1, a 1, and a 1. We get 2 heads 6 times, so we get 2, 2, 2, 2, 2, 2. 4 heads, 3 heads 4 times, there they are, and the 4 heads that we get once. Now I could have listed this as a frequency distribution, and if you go over 4 heads, you really would want to do this as a frequency distribution, but the meaning of a frequency distribution is just this, and if you actually sit yourself down and do this calculation just by listing all the numbers, the appropriate number of times, pretty soon you'll be motivated to invent a frequency distribution to do the problem, and then you really understand frequency distributions better than if you're just following formulas. So I'd stay close to the meaning, but of course if we go over about 5 heads, we're not going to list them like this. Okay, well, the mean of these numbers is 2. We could add the numbers up and divide by 16, but we can see very clearly that by the symmetry of this, we've got a 0 and a 4. Well, that's going to average 2. We got a 1 and a 3. That's going to average 2. And we have a 1 for every 3, so all the 1s and 3s are going to average 2, and every other number we got left is a 2. So there's no question that the mean of this set of numbers has to be 2. Well, and that's again a symmetry argument. Okay, deviation from the mean then. Because remember, the square root of, we're trying to find the square root of the mean of the squared deviations from the mean. Okay, now let's back up and see why we calculated the mean. If we try to deconstruct this statement, what's the first thing we have to do in order to perform this calculation? It's not take the square root, because we don't have the mean of the squared deviations of anything. It's not the mean of the squared deviations, because we don't have any squared deviations. We don't even have any deviations. Okay? So we're left, we have to find the mean. We have to find the mean first. And of course, we don't do a standard deviation in this course by just punching the standard deviation button on our calculator. That leads to no insight. Of course, obviously, there'll be cases for expedience you do that, but first develop the insight about what a standard deviation is. Okay, so we have a mean of 2. We have a deviation from the mean then. Well, how much does 0 deviate from the mean, which is 2. 0 deviates from 2 by 2. Now, one number deviates from another by how far that number is from the other. How far is 0 from 2? It's 2 units from 2. Okay? It's the absolute value, if you wish to do it, of 2 minus 0. Okay, well, deviation of 1 from 2 is 1. Deviation of 2 is 0. Deviation of 3 is 1. The 1 is 1 unit away from 2. 4 is 2 units away from 2. Deviation is how far away one number is from the other. We don't care if it's above or below. We're not going to get positives and negatives. And incidentally, that's one reason and I don't have the formula anymore. I've cleaned that board. But when you, well, I'm not going to digress that far. That formula that somebody used for the standard deviation should really have an absolute value in it so that we're actually representing a deviation. The result of the formula wouldn't be any different, but if you represent deviation in there with an absolute value rather than parentheses, you have more meaning inherent in the formula. Okay, and I think meaning is important in everything you do. In any case, so the deviations, well, we could list the deviations because we got 1, 0, so we have 1, 2. We have 1 that occurs 4 times, so we're going to have deviation of 1 4 times. 2 occurs 6 times. It has a deviation of 0, so we're going to have to write down 6 zeros. 3 has a deviation of 1. We're going to have to write down the 4 ones. 4 has a deviation of 2, so we're going to write down a 2 for that deviation. So here is a list of our deviations. Okay, well then, what are our squared deviations? Now, it wouldn't matter if you had -1s here and -2 here, since you're going to square these numbers. But again, let's keep track of what the words mean. The deviation is an absolute value of the difference of two numbers. And it's intuitively how far the numbers are apart. Okay, square deviations are clearly then 4, and then 4 1s, and then 6 zeros, 4 1s, and a 4. So we want the mean of the squared deviations. Looking at the definition, okay, we have mean, we got that. We have deviation from the mean, we got that. We have squared deviation from the mean, we got that. Now we want the mean of the squared deviations. There's nothing about sum in here, but how do you find a mean? You find a mean of a set of numbers by finding their sum, and we can add these up. We get 16, and it should be obvious. You got 4 here, and you got 4 1s, that makes 8, and then you got the same thing over here, another 8, that's 16. So the mean of the squared deviations is 16 over 16, which is 1. So now, what's the square root of the mean of the squared deviations? Well, it's very simple. The mean of the squared deviations in this case is 1, so the square root of the mean of the squared deviations is also 1. Square root of 1 equals 1. Now, I'll do the qualifier. This is the definition as I gave it to you, but it only applies to n greater than 30. Actually, n greater than or equal to 30. N is less than 30. N is only 16. You've only got 16 numbers. So the better answer for the standard deviation is the square root of 16 divided by 16 minus 1. That comes out about 1.03. Not very significant in its difference, although depending on just how precisely you want to get things, that might be a significant difference, but it's not a big difference. Okay? So now, excuse me. Well, now I want to use my normal curve. Unfortunately, I used the normal curve. I just got done looking for the normal curve that I did when I explained how to construct a normal curve, and realized that this is it. And I've already superimposed a histogram for 4 flips on that normal curve. And I'm going to have to digress and explain how to do a normal curve, how to construct a normal curve. So I'm going to do that in another video, and then we'll explain here. I have enough room down here that I'll be able to show you the construction of the normal curve in case you didn't see it. Then we'll come back and relate it to what we've done here.